Hello, this is a demo of marketing attribution done in Alteryx. And you can find marketing attribution code if you want in R. You can find it in Python. But I looked for it, I couldn't find it in Alteryx. So hopefully this is the first one. Probably not. I'm sure someone else has tried it. But this does marketing attribution analysis. Okay. To do this is my input, and it's using data that I created, marketing data that I created. This marketing data simulates a video game seller or a video game maker, like a Nintendo, a Ubisoft, PlayStation. No, not PlayStation. I don't know. You get the idea. Yeah, PlayStation. So the idea is that this video game maker is trying to market to their clients, and they send them emails. They send them social media announcements. They send them in while they're playing the game. They send them a little announcement saying, "Hey, you should try this. If you like this game, you'll probably like this other game." These are what we call in-game advertisements. They also have YouTube videos where they can demo the game, and they have Twitch videos. So Twitch, oh, by the way, is a platform for video gamers that actually just record video game players playing a video game. But anyways, so imagine that this video game company sends people an email, and in the email it goes ahead and it has a couple of links. They can either buy directly the video game, or they can go see a YouTube video, or they can go see a Twitch video. Okay. Likewise, they can get a social media announcement that has the same links that they can click on. They also can get an in-game advertisement where it also allows them to just skip it, or they can go to see a YouTube or Twitch video, or they can go direct and buy the game. So these are all the different types of options that players have when they get these announcements, these advertisements. And so naturally what happens is that some people are going to get it, they're going to get an email, and then they're going to say, okay, fine, I don't want to go see anything. And then later they'll get it, maybe a social media announcement. And they go, I saw that email, that's kind of like this. Yeah, okay, let me look at this. And let me look at the YouTube video. Oh, okay, that's kind of interesting. And they come back and then they make a purchase. Okay, so you'll see that there can be a different path for each person. One person may get an email, and then later get a social media announcement, and then based on that, go to see a YouTube video, come back, and then say, "Hey, fine, I'm going to go direct and purchase this." Or maybe it's they got the social media first, and then they get the email. Or maybe they got the in-game while they're playing the game. They got the announcement of this new game coming up, and they looked at that and they didn't think of anything of it. And then 2 weeks later, they get an email and say, "Oh yeah, I remember that game. That's really cool." Then they go off and purchase it. So you can have these different paths on the way towards a purchase. And what these paths are help us describe what is known as a state graph. Imagine each channel is a node in this state graph, and you go from state to state. So first I get the email, that's at one node. And then from there, I go to the next state, which is, hey, I get a social media advertisement. And then the next state from there, let's say I go to get the YouTube video. And then after that, I say, okay, I'm going to make the purchase. So I make the purchase after the YouTube video. So it builds these, what they call state graphs, of all the interconnected nodes, or the nodes are the channels. And it also calculates the probabilities if you go from one particular node to go to another node. So let's say you get the email, and then after you got an email, you got a social media announcement. There's a certain probability that you're going to react to the social media. You're actually going to look at it. There's also a probability that you won't. Okay. Well, if you look at this over thousands and thousands of people that actually go through these paths, you can calculate these probabilities. Okay. And so that's what happens in a Markov chain, which is Markov is a type of finite mathematics where we basically calculate the probabilities for all the different possible paths that you can go towards a conversion or a purchase of a video game. These particular programs, the programs that these use, calculate all these probabilities, and on top of that, they can then go back and for each of the nodes or each of the channels, calculate how much of the total purchases was that channel worth. And how they do that is really kind of cool. It's really cool. What they do is they calculate all the purchases that were made with all the channels. That's basically based on all the data that you got. Then after they build this little graph, they pull one of those channels out. When they pull it out, they can now calculate, they have all the probabilities for all the different other channels, and then they can go ahead and run simulations and say, okay, how many purchases do you get now that we pulled email out? Or how many purchases do you get now if I pull out the social media element? And then by doing that, if you're obviously going to get fewer purchases, but how many fewer? Well, that tells you how many purchases social media was actually worth, or how many email was worth in light of everything else. Okay, and this is basically what Markov model marketing attribution does. It calculates how much each of the channels is by removing the channel, recalculating, resimulating the whole graph, and seeing how many purchases you would have without it. It's really cool. Anyways, brought this into Alteryx. So now in Alteryx you can do this. I created two different macros to do this, and one was written in using R code, using the R tool, and that's this one right here. And the other one was written in Python. Why did I do both? I don't know, just for fun. So now the R code, or the one that uses R code, anyway, so here's the data. It comes in, it gets into this macro. Over here on the macro, you basically tell it, what are your different fields that you need. And by the way, here's what the data looks like. Let me show it to you. That's important. So here we have the path. Now the path shows you each of the channels, and it has a little separator, like a little arrow between them, saying, for example, on this one right here, we went from email to an in-game to social media to a Twitch video to another social media to a YouTube, and then he finally purchased. Or he purchased, or maybe he didn't purchase. But to figure out what exactly he did, we go over here. This is the number of people that went through this specific path, this unique path itself. We only had one person, and that one person did convert, so they did have a purchase. And nulls is the number of people that did not convert, that went through the same path. Okay. This here is the number of dollars that came from this one purchase. So this one purchase bought this game for $68. Okay. You can see here, for example, this path, it's a little bit shorter, went from email to in-game announcement to YouTube. We had 17 people that went through this path. 13 of them converted directly at the end of it. 4 of them said, no, not interested, and never came back. And for those 13 people that purchased, they spent a total of $956. Okay. This particular data set has 3,724 different paths that were simulated. Like I said, this is all data I created to simulate this, and it wasn't all random data. Trust me, I put in a lot of thought. I called my son, who's really big into video games and knows all the details. He gave me kind of idea of what are the sort of basic probabilities that people would purchase a video game based on, different types of advertising. So thank you. That's to my fourth son, Peter, for helping me out with this. But anyways, this is all the data that came as a result of that. And so we feed it in. So we got the number of paths, the number of people who went through that particular path, the number of conversions, the number of purchases, the number of nulls, which is the number of people that didn't purchase, that went through that path, and the total amount of money or revenue that they gained from all these conversions here. Okay. All right. So this is fed into this macro right here. This macro here, we just kind of identify what each of these fields are. Over here, I can do the configuration of the macro. First, I have to tell it what is the path separator between my different nodes on that path. I have to tell that, it uses the arrow, and that's what separates one node from another, or one channel from another. The order, the maximum order. This particular macro, what it does is it actually allows you to, it tries to figure out what is the optimal order of the Markov chain that it's going to go ahead and analyze. And you're probably asking yourself, what is order? Think of it this way. A first order calculates the probability you're going to go from one state to the next state. In other words, you go from like an email to an end game based solely on the one previous channel that you were at. So if you were at an email, email, and you go to an end game, then it's only basing that probability on the fact that you were at an email. A second order is based on the previous two channels that you were at. So if you got like an email and then a YouTube, and then what is the probability that from after those two are together, you go to a Twitch video. Okay, so that would be a second order. You can have a third order, fourth order, on up to. It actually kind of depends on how long your paths are. You could have a 20th order. If you've got 20 paths with 20 different steps in it, you could have a 20th order. For this particular node, it turns out that the most optimal order was an 8th order. However, and I say that only because it allows us to better predict what people are going to purchase in the end. But just for simplicity's sake, I put it as on my default as 1, because most companies are going to just use a first order because it's kind of hard to conceptualize beyond that. This is the number of simulations. What's cool about these programs, that the R program and the Python program that are these macros use, is they do all their work through simulations, which is a very smart way of doing it. I know that because I actually tried to make my own Markov program to do all the calculations necessary, and then I wanted to do this in Alteryx. I did it for a 3-node, or in other words, 3 channels, and it was fairly simple, and worked fine, not a problem. And then I says, well, let me throw in 6 nodes. 6 nodes, whatever, and see how it handles. So I did all the programming. Oh, it was horrible. What happens is my program, what it did is it would try, I set it up to where it would calculate every single probable path through 6 different nodes. And just in doing that alone, I was creating, I didn't even get 2/3 the way through the calculations, and I was already at 50 gigabytes of data as it's trying to calculate all the possible paths, and it was taking forever. So I said, no, this is not going to work. There's a better way of doing it. And what I realized when I went back and studied these packages, they are doing it the better way. And the better way is you just do simulations and let the simulations figure everything out, instead of you having to calculate all the possible paths and the probabilities for each of these paths and all that, like I was trying to do. So it uses simulations. That's what this whole number here is for. This is set to 500,000 simulations. If you use much more than that, if you've got a lot of data, the more data that you have, in other words, the more nodes you have, or the more channels you have, that type of stuff, you're going to want to use more simulations. If you only got 3 channels, you don't need to use 500,000. You can only use maybe 10,000, 20,000. But if you got a lot of different channels, you're going to want to increase this. Got 2 more parameters here. One's a convergence parameter, and the other is the rate step sim. These are to help converge on, when you're doing the simulations, you want to converge on an answer. So these help you do it faster or shorter. And people who do modeling will probably understand these a lot better. The last one is the seed value, and this just allows you to repeat, because it does simulations, Every time you do it, there's a bit of randomness, and you get just a little bit different results. If you use the same seed value all the time, it will guarantee those results for the same data will always be the same. So that's what the seed value is. So as you set this up, you let it run. You can do it over here. Now, okay, on the output here, just we'll go back to the output. Now here on the output, what you get is, let's move this over here. Here's my channel name. And here is the Markov model channel attribution amount. Now remember, in this particular data that I have here, in total there was 18,987 purchases. So what this model did is it went and it calculated how much of those purchases can be attributed to email. And that's what this line is. How many of those purchases can be contributed to or attributed to in-game advertising? How much of it is to social media, YouTube, Twitch and YouTube, okay? And then these are the percentages associated with that. You add them all up, you get 100%. It also gives you, as a bonus, 3 other types of attribution. In the attribution world, you don't have to use Markov modeling. In fact, a lot of companies don't, because they don't understand it or they don't know about it. I don't know. But they kind of come up with a heuristic way of doing their attribution. So, for example, I know of some companies, for example, when you go buy a car at a dealership, what happens is who gets all the credit for the sale when you buy the car? It's the first person who talks to you when you walk through the door. That's the salesperson. That first salesperson that contacts you gets the vast majority of all the attribution of the sale. Okay, and they know they need to know this because they got to give him the commission for the sale. So a car dealership uses first touch attribution. The first touch is the most important, and that's what this symbolizes here. Where some companies would, if the first thing that got you interested in a particular product was an email, then hey, that is the one that's going to get 100% of the attribution. Some companies use the last touch, and the last touch is what was the last channel that you were touched with before you made a decision to purchase. And the feeling is that was the one that kind of pushed you over the edge. That's called last touch attribution. And so if you did a last touch attribution, this is how it would break out here. Other companies say, we don't like the first touch or the last touch because it kind of doesn't give credit to all the other touches in between. So what they do is they do what they call linear touch. And what that is they evenly distribute a purchase to all the different types of touches that hit it before. So if someone had an email, an IG, and a YouTube, those 3 would get 33% of the attribution for that revenue and for that purchase. Okay. However, the most accurate model for doing or method of doing attribution is right now is the Markov model. There's a few other types. You can use linear regression, which I've done before. You can use logistic regression as well. Not as good, and that has partially to do with the fact that linear regression and logistic regression can very easily end up with negative coefficients. It's hard to describe, but bottom line is you could end up doing getting negative values for the attribution, which you really don't want. It doesn't make sense, but it's just the way the modeling works. So these show you for the number of purchases how those purchases get attributed. Over here, we do for the first touch, last touch, linear touch, and the Markov, we split up the total revenue. So you notice at the bottom, it gives you the total revenue, which was $1,417,443. That gets split up in the first touch method this way, the last touch method this way, the linear touch method this way. But if you use the most accurate way, which is Markov model, it gets divvied up this way. Okay, and then this is the percentage of that, which correlates to the percentage over here. So that's on the output of this. On the R, I also give some graphs, some histograms. I just basically take the same data and I histogram it. So you can see here, here's the total revenue broken out by the different types of touches. The red is the first touch, green is the last, turquoise is the linear, and the purple, my favorite, is the Markov. Total number of conversions, and then this is a penalized AUC curve, which you don't see it filled in right now. But when you're using higher order models, models of Markov, like an 8th order or a 9th order, 10th order or something, it uses the AUC to kind of determine which is the most optimized order by the AUC value, because it wants to choose the minimum order that gets you the highest amount of on the AUC curve, which is the most accuracy in predicting the output. This next is what we call the transition matrix. This is like if you're on that state graph I was telling you about, let's say you just got an EM, this calculates what is the probability that if you get an in-game announcement after you've already received an email, what's the probability you're going to react to the in-game? What's the probability you're going to go from an email to a social media or a Twitch or a YouTube? So this is what we call the transition matrix. The next thing is just shows the different configurations that we used. I put this on an output so we can use those configurations if we need. But anyways, I've got two different macros here. One uses the R version called channel attribution, and I'll show that to you right here. So this is the actual inside of the macro. Move this down here. All this part here allows you to do the configuration that is needed, and then everything goes into the R tool where the real magic happens. And the real magic happens inside this program called channel attribution. I'm going to call out the name of the person who authored it because I think it's important that they get some of the credit. They should get all the credit. It's David Altomar and David Loris, who created this R package called channel attribution. Like I said, it works on simulations. I don't know exactly, I haven't seen the code for it, but I know it works on simulations, and I do imagine that they do a lot of the work in linear algebra in trying to manipulate all the transition matrices and the input matrix and all that. So a shout out to them for creating this package. And the latest version of it was created just a month ago, 3rd of April 2020. So this is what it looks like. This is the Python version, which looks very similar. It has fewer bells and whistles. By the way, the Python version was created by a guy named Jason Wulsanovich. I hope I said that right. And it's called PyChatter, Pychattr. And according to the research, I went to his GitHub page, downloaded it, everything, and read a bunch of stuff. It appears that what it is, PyChatter, is just a Python wrapper around the channel attribution R code. So they took the channel attribution R code, put a Python wrap around it, and it says, okay, here's Python. It's cool. It's all right. But it still is dependent on the channel attribution, which is written in R. Okay. I think because channel attribution that was written in R, the latest version just came out a month ago, and PyChatter, their version came out a little longer than that. I think it's obvious that PyChatter was using an older version of the R version of channel attribution. So it doesn't have as many bells and whistles as the latest version of channel attribution in R has. So because of that, I don't have as many configuration parameters that you can use when playing around with this. But anyway, so here's all the Python code for this, where I just take the input and set everything up. And this is all in a Jupyter notebook inside the Python tool. And then here are my outputs over here. All right, so getting back to here, Python, again, we've got the same table as we had with the R code, and when I compare the two with the same data, they're comparable. So hey, it tells me that the folks who did the R wrapper did everything correctly. It's doing everything well. One of the outputs that I got from the Python that is kind of cool gives you the removal effect. Remember, I said when you're calculating the attribution, if you remove the node or the channel, then you go back and you throw a bunch of simulated people going through the paths, and then you see how many purchases were made. You then can tell how many purchases were made with that channel and without that channel, and that gives you an idea of how worthy or how much worth you should associate or attribute to that channel. Well, this table here gives you the removal effect, which is important in calculating that worth. So that's kind of cool. This is the transition matrix, which is the same as we saw before. And yeah, for the same data, it comes out the same. So that's good. And then finally, this is the parameters, the configuration parameters that I put on the output as well. So there you go. If you want to use Alteryx for doing marketing attribution, I got a solution here, and it works like a charm. So just get in contact with me. My name's Clifford Jordan, and you can probably find out who I am through the Alteryx community, or you can find out who I am through my YouTube channel. Thank you.